All right, so we've already talked about how to graph square root and cube root functions themselves using our parent patterns and the transformations. So today we're going to look at how we can solve square root and cube root equations graphically, as well as just some real-life applications of the square root and cube root graphs themselves. So example 1 says the whole speed h in knots of a boat given by the function h of x equals 1.34 times radical x, where x is the length of the boat measured in feet at the water line. So h stands for whole speed here, x stands for the length of the boat at the water line. So it tells us here in A that the whole speed function is a transformation of our parent graph, and it asks us to graph them both on the same axes. So this is just review from what we did the other day. Our parent pattern for the square root function is 0, 0, 1, 1, 4, 2. So if I'm graphing my f of x, the parent function, I would use those same points. So 0, 0, 1, 1, and 4, 2. So this, and I'm actually going to plot an additional point at 9, 3 just because it goes up that far, so that way we can get kind of a more accurate shape. So there's our parent. So our transformation here, of course, has an a value out in front. 1.34 is the only change to the parent graph that we have. So when we look at these and we're graphing them, part B, compare these graphs with transformations, we would say that h of x is a vertical stretch of f of x, our parent, by a factor of 1.34. So of course, we're not used to, having decimals here because usually these are problems that we're doing by hand. Here with the decimal, we would definitely be allowed to use a calculator. This is a real life situation, but I just want to show you that what we're doing is really the same thing. So a values get multiplied in our parent pattern, so times 1.34 on all of these, which that actually should not be difficult to do by hand if we needed to, but we get 0 here, we get 1.34 here, and then we get 2.68 here. So our h of x function starts at the same point at 0, 0, but then we have right 1 up 1.34, so just a little bit above where the other one is, and then right 4 up 2.68. So you can see that as time goes on, the gap between them is going to get a little bit bigger. So this one right here is our h of x. In the purple, that's our transformation. So part C is important because this goes to interpreting a real life situation. Given that x represents the length of the boat, should the domain of h of x be more restricted than that of f of x? So in our first lesson in this unit, we talked about domain and range for both square roots and cube roots, and we had said that the parent domain, so f of x's domain, is from 0 to infinity. And if we look at the domain of h of x just from the graph, it would have the same domain because x's start at 0 and they're getting bigger. But here, what we really have to think about is that the domain really isn't totally based on the graph. It's based on what makes sense in the real life situation. So x represents the length of a boat. So can the length of a boat really be 0? No, because then there wouldn't be a boat at all, which doesn't make sense for the real life situation. We can also definitively say that there has to be an upper limit. We can't have a boat that is truly an infinite number of feet long. There is some sort of limit that is going to, keep it afloat and all of those things. So this answer is obviously going to be yes, because it can't equal 0, and there has to be an upper limit. Now, we can't list what that restricted domain would be in this case, because we don't know, what the limit is on maximum length of a boat that would still keep it floating, or minimum length for that matter. How small could you make a toy boat and still have it actually create a boat? We don't know that, but we do know it has to be bigger than 0 and that it can't be infinity either. So we've got an upper limit, we've got a lower limit. So we know it has to be more restricted because of the real life situation. So that's always important when we're talking about interpreting. Part D says, how would we write g of x equals the square root of 2x in the form a times radical x? And then what transformation is represented by it? So this one we are addressing for a very specific reason. When we did our first lesson, in the general form equations that I wrote, for the square root, we just wrote this, a times the square root of x minus h with a plus k on the end. And what I had said is that we don't have any b values. And so I told you, don't list horizontal shrink or stretch as a transformation on these radical functions because we aren't going to have them. The reason we don't have them is because of this question that we have right here. If I have the 2 underneath the radical, because of the way that radicals work, and we spent a good bit of time reviewing how to simplify and deal with radicals back in Unit 2, the square root of 2x, I can separate that into the square root of 2 times the square root of x, which actually then is now in the form a times radical x. So now I've taken what looked to be a b value of 2 and made it an a value of radical 2, which means, because it's an a value, that now it's the same transformation as every other a value. It's not negative, so there's no reflection. The square root of 2, which is about 1.4, is bigger than 1, which means this represents a vertical stretch by a factor of radical 2, or 1.41 approximately. So that's why we're never ever listing b values, because what you're going to do is, if you see the number on the inside, you're just going to separate it and bring the radical along to make it an a value on the outside. So that's another really important piece of information to understand, because you'll definitely have some of those as we move forward. So part E, we're getting into actually solving graphically. So part E asks us to estimate the hull speed of a boat that is 24 feet long at the waterline. So again, hull speed is the h. So it wants to know h. So I'm just going to write this out. Find h when x, because x is the distance, is 24. Now, our graph certainly doesn't go up that far. You could graph it by hand and just continue it if you wanted, but of course, it's much, much easier to just use our graphing calculator. So if you don't have your calculator out, you need to get it out. And you are going to type the h of x function into your y equals screen. So here I'll bring up mine. So you can see my y equals screen here, 1.34 times radical x. You can also, because mine shows you both windows at the same time, you can also see that the graph does, match what we had in our graph. And if you go to second graph, we can look at the table and see, oh, voila, at x equals 4, we did correctly multiply that value to get the correct point to plot. So again, this is asking us to find h when x is 24. So we've done this feature of our graphing calculator tons of times. We go to second trace, choice 1 for value, and now I can type in any x value that I want. So I'm going to type in 24. I'm going to press enter. Now remember, if your window doesn't go up past 24, it's going to give you an error message that says error window range. That just means go to the window make sure your x max is bigger than 24, because if it's not, that feature of the calculator won't work. And of course, I didn't write it down before I closed out of the window. So there we go. So we can see the y value when x is 24 is 6.56. So that would be about, it doesn't say what to round to, so we would say that h is approximately 6.6 knots, because it told us that the whole speed was measured in knots. So again, if you want to write down what we did, we went to second trace, choice 1, which was value, and we typed in x equals 24 and then enter. So when they give you an x coordinate and they're looking for the y, second trace value is what we're going to do there. So part F is different because this one wants us to estimate the length of the boat at the waterline when the whole speed is 6 knots. So not only is it a different type of equation in the calculator, but this also asks us to write the equation represented by the situation in both radical and rational exponent form. So when I look at this, whole speed is h, so that's 6 in this case. 6 equals, what I'm looking for is the length of the boat. That's my x. So I'm just taking the whole speed equation and simply plugging in 6 in place of h. So this would be the equation in radical form. In rational exponent form, remember the only thing we're going to change is instead of square root of x, we're going to write x to the 1/2 power. And so to actually solve it, you can do it algebraically if you want to. We're definitely learning how to do that in this activity, but it's easier to do in the graphing calculator because all I need to do is go back to my y equals screen, type in 6 here, press graph, and then find the intersection point. So we've done this a bunch of times this year too. Second trace, choice 5 for intersect, and move your little cursor so that it's super close to the intersection. And then, yes, that's my first equation. Yes, 6 is the second equation. And yes, I would like you, calculator, to guess. So it's telling us the intersection x coordinate is 20.049, and the y, of course, is 6. So that tells us that x is approximately 20 feet in length to get that appropriate whole speed. All right, so same idea in example 2, except now we're kind of looking at a cube root function instead of a square root function. So it gives us r of x, and it's a cube root, and it represents the length of the radius of a sphere as a function of its volume x. So x is the volume, r is the radius. And here they're giving us an approximation cube root of 0.24x. So in the notes, we're pointing this out to you. It's not always pointed out to you here. This is underneath the radical symbol. Just like we did up here in 1D, we need to simplify that. Now again, you don't have to simplify that by hand. You don't have to know what the cube root of 0.24 is off the top of your head. Do it in your calculator. Remember, the cube root button is in your math menu, math choice 4, and type in 0.24, press enter, and then now that gives us what it is as an A value as opposed to being a B value on the inside. So the cube root of 0.24 is about 0.62. So that means that r of x equals 0.62 times the cube root of x, and rational exponent form, r of x equals 0.62 times x to the 1/3 power. So what transformation is this from the parent cube root? So obviously it's an A, which controls vertical shrink and stretch. In example 1, it was a stretch because the square root of 2 is 1.41. It's bigger than 1. Here, this is going to be a shrink because 0.62 is less than 1. It's a fraction between 0 and 1. So we're going to say that that is a vertical shrink by a factor of 0.62. So then last one, what equation would you solve to find the radius of a sphere that has a volume of 6 cubic units? So the volume, remember, is x, so we're solving that r equals cube root. Actually, we should use the simplified one. So 0.62 times the cube root of, in this case, cube root of x, which would be 6. So this would be our equation. In this case, our variable is already by itself. So solve it using your calculator just means we need to punch this in. So we've got 0.62, and we're going to multiply that by the cube root of 6, so 0.62 times the cube root of 6, press enter, and we get about 1.13 there. So radius is approximately 1.13. So it asks us to show a sketch or an explanation. So in this case, if we want to show a sketch, we would sketch the graph itself. So go to our y equals screen. We can get rid of the other ones from example 1. And we've got 0.62 and then cube root of x, enter, graph. And we can see this is a very small graph because of the shrink, so I can adjust my window. I don't need it to go quite as far or quite as high here. So we went up to 15 before. I can probably just really go up to 5. And so now, if I draw a sketch of the graph, 2, 3, 4, 5. And we look at it, really at 5, we're only up to about 1. So right 5, up about 1 here, 0, 0, and then same thing on the other side. So it's going to look like this, and so in this case, all we're doing is we're finding in our sketch here where x equals 6. And again, if you were doing it with the graph in the calculator, second trace value, you would type in x equals 6, and look, we get the same answer that we did just on the home screen of our calculator. All right, so hopefully that refreshes your memory as far as how we need to solve these. So ones where you're given x and looking for y, we're using second trace choice 1. When you're given the y, you use second trace choice 5 for intersect. And this video will be on the website as well, so you can come back to it as many times as you need.